Okay, I'd like to start today with a warm-up. So if you will, just pause this and take a minute to look at these questions and give your response, and then unpause the video and see what your response should be. Okay, on the first one here, it says what important group was not able to testify. So in looking at this particular situation, those that did not survive the crash would not have had any impact into the survey that was being conducted. So that particular group was not able to be included in that survey. So on the next one, it was talking about Christmas trees. This one was a voluntary response survey and would definitely produce a biased result because of that. So, and then the last one, this one was a self-interest study because Mars was funding the study, and therefore, and it was a study about a chocolate and the benefits of chocolate. So that particular, the fact that Mars was benefiting from that would create a bias, could potentially create a bias. Also, correlation does not imply causation because the study was trying to say that the chocolate reduced heart disease when in fact there really was just a correlation and not a cause-effect relationship established there. Okay, so in section 1.2, we're going to look at different types of data today. Okay, first of all, you should be able to identify the difference between a parameter and a statistic. Parameters come from the population, so both of these are numerical measurements that describe some type of characteristic. The part that differentiates between the two is whether they come from a population or whether they come from a sample. So in looking at this, we've got the parameter starts with P and it comes from a population, which also starts with P. A statistic starts with S and comes from a sample, which also starts with S. So that's just an easy way to remember which one which two go together. Okay, so here's a couple examples I'd like for you to take a look at. We're going to do the first one together, and then we will, I'll let you have some time to look at the others. So the first one, all business majors at Wingate University were surveyed, and it was determined that the average GPA of all business majors was 2.5. So when we look at 2.5, 2.5 is the average of all business majors. So the fact that it's coming from all business majors tells me that that would be a parameter instead of a statistic. So take a look at these underlying values for just a minute and determine whether the underlying values would be parameters or statistics. Okay, looking at these, this one, number 2, 10 randomly selected people were asked how long they slept at night. The mean time was 7.1 hours and the standard deviation was 0.78 hours. Both 7.1 and 0.78 are values that are coming from the 10 people that are randomly selected. So here our population is basically all people. The sample is the 10 people, and because of that and the fact that these two are coming from those 10 people, these would be statistics instead of parameters. Okay, the next one, a survey of 30 adults found that the mean age of a person's primary vehicle is 5.6 years. So if we look at this 5.6 is coming from the 30 adults, and the 30 adults represents our sample. Therefore, this would be a statistic. And then it goes on to say, assume the population is normally distributed. Assume that the standard deviation of the population is, sorry, 0.8 years. So in looking at this 0.8 years here, that because that's coming from the population, then it would represent a parameter. Okay, another way that we distinguish data is quantitative versus categorical. So quantitative data is your numerical data. This consists of numbers that represents counts or measurements. So this example will be weights of supermodels, ages of respondents, how much people make in a year, their SAT scores, things of that nature are all going to be quantitative data. We look at categorical. Categorical data can also be called qualitative or attribute data. This is data that consists of names or labels, but not numbers that represent counts or measurements. So this would be things like gender, shirt numbers on professional athletes' uniforms. It could be your religious preference. It could be your political preference. It could be all kinds of different things. And it can be numbers, just not numbers that represent counts or measurements. So, for example, your social security number, your student ID number, your telephone number, your zip code, your address, all of these are different cases where numbers are serving more as a label than any type of count or measurement, and they would be considered categorical or qualitative. Okay, so when you work with quantitative data, we differentiate between discrete and continuous. Discrete data is data values are quantitative and the number of values is finite or countable. So basically, if you can go in and count your data values, then it's going to be discrete. And the formal mathematical definition of countable, you can count on forever, but there is a one-to-one correspondence there. So anytime you're counting, versus measuring, it's going to be discrete data. For example, the number of tosses of a coin before getting heads, that would be representing discrete data. If we were in the classroom, the number of desks in the classroom would be discrete data. The number of cars that pass through a stop sign on a given day would be discrete data. Continuous, by comparison, is when we have infinitely many possible results. Okay, so we can have, like, maybe if we're measuring somebody's weight and we had the old scale type where you move the little thing along the top there, then what happens is you might do good if you get to the nearest pound, but maybe you have a digital scale and maybe you can get to the nearest tenth of a pound, or maybe the nearest hundredth of a pound, or the nearest thousandth of a pound. So because there's infinitely many possible values that you can get when you're measuring something, those are going to represent continuous data situations. So example here, if we want to measure the length of distances from 0 centimeters to 12 centimeters, because we're not just counting off in centimeters, we could have like half a centimeter or a tenth of a centimeter. There's infinitely many lengths that could be between 0 and 12 centimeters. So if I'm measuring something, that's why I said think measurable. If you're measuring something, it's usually going to be continuous data. If you're counting, it's going to be discrete data. Okay, so we also have levels of measurements. We have 4 different levels of measurement: nominal, ordinal, interval, and ratio, that I would like to go through here. Nominal is the most basic. It's characterized by data that consists of names, labels, or categories. So this is our categorical data or our qualitative data. It can't be arranged in some type of order, such as low to high. So example, we're talking about political preference, maybe Republicans, Democrats, Independents. We really can't arrange those in any order of being low to high. Or if we're looking at religious preference, Methodist versus Baptist versus Catholic, there's really no order to that, and so that would be nominal level data. Survey responses such as yes, no, and undecided would also be examples of nominal data. Ordinal is where we start having some order. Okay, it involves data that's arranged in some order, but the differences obtained by subtraction between data values either cannot be determined or are meaningless. So for instance, if we're looking at course grades, obviously if you make an A, you've done better in the class than somebody that made a B or somebody that made a C. But the difference between an A and a B and a B and a C may not be the same, because because you have an A, you might have a 99, but on a B, you might have an 89 or an 81. We don't really know. And so the differences really either can't be determined or really aren't meaningful. We just know that one is better than the other. So anything that orders, puts it in like a ranking, like somebody came in first in a race and somebody else second and somebody else third. We really don't know what the difference between first and second and third was. We just know that one came in faster than the others did. Interval data involves data that can be arranged in order, and the differences between data values can be found and are meaningful. However, there's no natural zero starting point. So an example of this would be temperature for one, because if I'm talking about Fahrenheit, 0 degrees Fahrenheit is not the absence of all heat, and therefore it is not considered as natural zero starting point. So same thing with Celsius. 0 degrees Celsius is not the absence of all heat, and therefore the Celsius scale would be considered an interval level scale because it has no natural zero starting point. Now, for those of you familiar with the Kelvin scale, 0 degrees Kelvin is the absence of all heat, and so that would not be interval level data. Another example would be the years. And when I'm talking about years, I'm talking about calendar years. Because if in looking at this, we know that there were years before year zero, and therefore the year zero is not a natural zero starting point. So to be a natural zero starting point, it has to be the absence of that quantity. Okay, so the two that I would mostly remember for interval level data are temperature and years for that. Okay, ratio data is the most mathematical, and this is kind of the highest level. It can be arranged in order, differences can be found and are meaningful, and there is a natural zero starting point, which indicates that none of the quantity is present. So we have lots of examples of ratio level data. The class time in minutes in your class, if a class is 50 minutes and another one's 100 minutes, then one is twice the length of the other. So that type of thing. But if we're looking at degrees Fahrenheit, because this is interval data here, 32 degrees is, or 64 degrees is not twice 32 degrees as far as the amount of heat present at that time, because the 0 degrees Fahrenheit is not a true natural zero in that respect. The ratio data might be things like somebody's salary, their blood pressure, that type of thing. So a lot of the data that we're going to work with in this course will be ratio level data. Okay, so this is just kind of a summary. Nominal is your categories only, ordinal categories with some order. Interval, you have differences but no natural zero starting point. And ratio basically has everything up through that. Okay, so here's a few for you to look at. So I'll pause this and then try to answer these and determine if they have nominal, ordinal, interval, or ratio, and then unpause it and see how you did. Okay, so if we look at rankings of movies by Rotten Tomatoes, because this is ranking in order, it's going to be ordinal. So just remember order, ordinal go together. That's kind of an easy way to remember it. Hair color would be nominal because it would be categorical data. Hair color would be like brown, black, blonde, whatever. So those would be your nominal type data values. Ranking of college basketball players for the NBA draft, you're putting them in order, so it would be ordinal. The body temperatures of children are generally measured in Fahrenheit or Celsius, so that would be interval data. Elementary school that you attended would be nominal because that would be like a label for you as to where you attended elementary school. And then salaries earned by doctors would be ratio data there because there would be a true natural zero for that. Years of experience teaching. This would be a ratio data as well because 0 years of teaching would literally mean you have no experience, and so it would be the absence of that particular quantity and would be a natural zero for you. The year that a movie is released would be interval data because the year that it's released goes back to the calendar year, and therefore those are interval data readings. Okay, I want to just quickly mention about big data. Big data, we're getting into an age of big data where we have really large data sets and they're very complex, and it takes running many computers simultaneously in parallel in order to be able to analyze the data. So there's a whole new field of data science that's coming out that involves applications of statistics and computer science, software engineering in different fields. And so this just might be something that you're interested in that you want to take a look at. Walmart and Amazon, Facebook, all of these deal with mega amounts of data. Here you see Walmart has a sales database that has 2.5 petabytes, which you can see that number of data, and they're processing this all of the time. They came up with their own search engine to increase their sales in order to work with all that large amount of data there. Amazon tracks 1.4 billion items, and so you can see the need for being able to analyze large amounts of data. So lots of job opportunities at some of these places analyzing the big data. This is to the end of section 1.2.